Okay, Miss Howard's Chemistry class, Borger High School Chemistry, Unit 10, Gases and Kinetic Molecular Theory, Part 2. So the state of Texas says you still have to be able to describe and calculate the relationships between volume, pressure, temperature, number of moles. You have to be able to do some stoichiometry, perform stoichiometry calculations, dealing with the mass and volume relationships between reactants and products in a chemical reaction. You have to describe what the kinetic molecular theory states, and you need to understand some basic forms of energy. So Roman numeral number 4, pressure. Pressure equals force divided by area. So when we talk about pressure, we're talking about the fact that it's caused by the collisions, the crashes between the gas particles and the container that it's in. So if you have a really weak container, the more pressure there is, you can break that container. Like if you have a balloon, if you put too much air in it, too much air pressure, then the balloon will bust. So what about when you don't have a container? Like you step outside and you have, if you're at sea level, 7 pounds of air per square inch on your body. Well, you are actually part of the container. The atmosphere, our air that's here, is kind of contained within, you can think of the outer levels of the atmosphere down to the ground. And you are part of the ground, part of the container. So whenever those molecules of air hit you, you are feeling the pressure. So when you talk about greater air pressure or lesser air pressure, you're not talking about more force, the molecules smacking you around with more force. You're actually talking about the fact that there are more molecules hitting in a smaller amount of area. So when you increase the air pressure, it's like you condense the molecules so they're closer together, and now instead of, say, 5 molecules hitting up per square inch, you have 25 molecules hitting per square inch. And that means you've increased the pressure. So pressure is force per unit area. Okay, so we look at our next chart. Which shoes create the most pressure? Well, let's say we're talking about one person wearing the shoes. So if she wears the first pair of shoes, look at the area that the bottom of the shoes cover. Compare it to the area that the second pair of shoes cover, and then compare that to the snowshoes on the right, where you've got a much greater area. So it's force per area. So the most pressure is going to be put on by the little heels over there because they have a smaller area. Okay, number 4, gases move from areas of high pressure to areas of low pressure. Always. They're always going to move. It's similar to diffusion. Diffusion is movement of molecules from an area of greater concentration to lesser concentration. And you have the same basic thing going on here. Gas molecules move from an area of high pressure to an area of low pressure. Pressure is measured in atmospheres, millimeters of mercury, or torr. It's got several other things it's measured in too. And we use a tool called the barometer to measure the air pressure. Okay, we have a video. Let's see if it works. And I haven't figured out how to edit it so my face isn't down there in the corner. One of these years I'll be able to block that out. But otherwise now I'll just be staring at you while you're watching the video. Yay!
The mega twister tore at the Earth for an hour and 25 minutes and left a devastated swath almost 40 miles long. But where did this energy come from?
Look down at this live picture of the helicopter, and I see this residential area that's been decimated. At that moment, I thought everyone's dead.
The wind speed was at least 270 miles per hour at ground level. Why was such force concentrated at times in a space the size of a football stadium? To understand the nature of these killers, we must begin at the beginning, 4.5 billion years ago. When the Earth first cooled, it was much like the moon. No atmosphere as yet. No local weather, no national weather, no weather. An atmosphere eventually formed, and more gases seeped out of the Earth's crust. Finally, comets brought us more water. They contain a great deal of ice. Over the eons, comets crashed into the barren surface. Gradually, the meltwater helped turn our planet into the blue orb we call home. The Greek philosopher Aristotle was one of the first to theorize about weather. His writings gave rise to the term meteorology. The Greeks decided all things were made up of basic elements: fire, earth, water, and air. Chemists have identified more than 100 elements now, but the ancient theory is still a simple way to think about the basics of weather. Fire. The fire that energizes weather is the nuclear fire of our sun. Earth. The Earth's surface is both the stage for weather, and it conducts how weather moves across that stage. And wind. And water, in all its forms, make up the essential substance of weather. Heat from the sun is the force that powers the engine of weather. Heat makes air molecules vibrate, bounce off each other, expand. Because heated air is thinner, lighter air, it rises. The atmosphere behaves like a fluid, a river of air with currents and pools and eddies and swirls. The atmosphere is endlessly moving from high pressure to areas of lower pressure. 400 years ago, philosophers were having a difficult time with the concept that air, invisible, had pressure.
The theorists of the time began to think of the atmosphere as, by analogy, basically a pile of feathers. If you piled in a ton of feathers into a space, you would have compressed feathers near the bottom that would get very tight. And then you would have relatively less and less until you had feathers that were almost blowing away in the wind at the top.
Scientific knowledge flowered during the Renaissance, and an effort was made to detect and measure air pressure. Evangelista Torricelli, one of Galileo's assistants, created the first mercury barometer. When the weatherman says the barometric pressure is at 29.5 inches, it means that the air pressure could push heavy mercury 29.5 inches up a tube, like the one invented by Torricelli. Earth, fire, wind, and water. Water plays a key role in our daily weather as it retains and releases the heat energy from the sun. Water is an energy conveyor belt. For instance, when the sun's heat dries up a puddle, that water turns to invisible vapor. Most of that energy, the equivalent of 1,000 light bulbs burning for an hour, is now in the vaporized molecules, once the average puddle has dried up. Wind can then blow that stored energy somewhere else, where it is released. The invisible becomes visible as the vapor condenses into a cloud. The energy released when water turns back into a big thunderstorm is mind-boggling.
let's go back. Okay, now that you can hear me, STP, standard temperature and pressure. At sea level and 0 degrees Celsius, we talk about standard temperature and pressure. Now, the atmospheric pressure, it can be 1 atmosphere, it can be 760 millimeters of mercury, or it can be 760 torr after Torricelli. It can be in pascals, kilopascals, psi. You know, we can talk about it in different things, but basically, STP, standard temperature and pressure, is 0 degrees Celsius and 1 atmosphere. Okay, Kelvin temperature scale is the same as Celsius, only they move the 0 down so that there would be no negative numbers. This is where you hear about absolute 0. Absolute 0, nothing's below that. It's as cold as it could possibly be. All molecular motion has ceased. So to go from Celsius to Kelvin, all you have to do is add 273. So if you have negative 10 degrees Celsius, add 273 to that, and you get 263 K. To go from Kelvin to Celsius, just subtract 273. Oh, and we have our last little video here. And let us play. Bill Nye the Science Guy.